Welcome back for another episode of High Performance Engine Building, classroom style. Today we're going to do camshafts and valvetrain. The valvetrain consists of everything from the crankshaft to the valves. So as we go through the system, that's going to be our timing set. Whether this is a chain or a belt, the gears, that kind of stuff. That's going to directly drive our cam, and our cam is going to have lifters or followers. If we got a lifter or pushrod style, next up is our pushrods. If we're overhead cam, usually our followers are acting directly onto the valve at that point, or if it's just like a lifter and bucket setup, will be directly at that point. But if we're pushrods, we've also got our rocker arms, which would be the same as our followers if it's an overhead cam deal. And then now we're acting on our valve. These are the direct parts that the forces are moving through to get that valve to open. But along with that, we've got our spring, retainers and locks, or seats for our springs between the spring and the head if we need them. Cast iron heads usually don't need them. Aluminum heads do, because otherwise the spring, it spins while the engine is running and that'll dig into the head. So that's why you need to have seats. Now it's just kind of a spacer material in there. It's not actually acting on the movement of the system, but it is something that is required. Start with our timing set. Now if we're looking at a typical V8, we're going to be able to have a chain. Usually there's a double or single roller. Usually a lot of the factory stuff is just single, and we like going to a double roller. A lot of the single stuff isn't even a roller chain setup, it's just a link. We can also have a gear set. These got popular back in early blower days, where they were driving, I believe, probably the fuel pump off of the camshaft, as well as maybe a gearbox to run multiple magnetos and all kinds of other crazy stuff, dealing with the old school blower style things. You can still get gear sets. They are a lot more picky about how they get set up, like the spacing's got to be right. They're also noisy because they're straight cut gears, so that's why you get kind of a supercharger whine from them. And they even got different cuts where you could choose how loud the noise is, kind of a thing. A lot of times this is not a choice we make nowadays, simply because a gear set like this also transfers harmonics. Now, harmonics being vibrations and just the way material is moving around of the crankshaft and rotating assembly moving makes a harmonic into that system. Well, if we're gear driven the whole way, we've actually got metal touching metal all the way up to our camshaft, and those harmonics can travel up into the camshaft and therefore into the valvetrain. And I've never actually gone through the whole process of finding out, but plenty of people that have had way more time and money to invest into racing programs have seen and found that those harmonics can get up into the valvetrain and either break parts or cause valve float or just problems in general. So really, a gear type set is not something we would choose in this day and age, but there still is kind of a place, especially for nostalgia, reasons or just, because somebody wants to as far as this stuff is concerned. There's also a belt drive. Belt drives are definitely more of a modern introduction, starting out with OEM cars. You can still get chains and belts in OEM stuff there. It's just kind of what the manufacturer decided to do. Belts really started coming on the scene in the 90s, maybe the late 80s, kind of a thing. And in more recent years, like probably in the last 15 to 20 years, they've been available as like an aftermarket timing set upgrade for V8 stuff there. I think the one I can think of off the top of my head would be Jessel, that does a belt, and the big motivator behind doing the belt is getting rid of those harmonics that the gear set is so prominent of. The chain doesn't transfer nearly as much because everything's kind of a movable piece, versus being solid gear touching solid gear touching solid gear. The belt lets things, it stretches a little bit, it flexes a little bit, which is kind of a downside, but they are pretty tough built belts. But your chain also stretches and flexes. So the belt actually is probably a little bit better at being less flexy, just because the weight of the belt itself is much lower than what the chain is. So the inertia forces of coming off of a small gear or crank gear to our cam gear, as we've got our chain or belt going around, and everything's rotating in this direction. If we're looking at it from the front, there are some engines that spin the other way, mostly like a front wheel drive kind of application. I believe it depends on which way the motor's playing. Some spin the other way, but your typical American V8 is going to spin clockwise when looking at it from the front of the engine. Well, the belt or the chain has weight, and because the crank is turning, it's really pulling this edge very tight because of the drag of the valve train system and the cam itself. But when it comes around, we've got the weight where the chain weight, if the slack in the system, because there's always going to be just a little bit, is trying to throw the chain out this way. And the same thing happens with the belt. But because the belt is lighter, it's going to be thrown less. And in theory, what we're trying to do is we're trying to make sure that the slop in the system is kept to a minimum, because as this pulls tight, the chain or belt might actually start out like if it was not running in a place like that where it's even on both sides. Well, as we're accelerating, we're pulling it tight, and we're getting slack on this side. But if we're lifting off the gas, slowing down, shifting a gear, whatever, now all of a sudden the crank is going slower in the valve train, and it reverses. We now get pulled very tight on this side, and we're being thrown with slack on the opposite side. Now, we're talking trying to keep this to very much a minimum. It all depends on how the chain or belt fits, because there's a very specific center to center distance between our crank and our cam that is supposed to be maintained. But if we've done any machining to our block, whether it's line boring or line honing, we might be making this distance shorter, or maybe it was a little bit short from the factory kind of a thing, where now our center to center distance is short, and that makes more slack in this system. Now, because of that, depending on the application, you can get some like -5 or -10 timing chains that just ever so slightly, like one link is just ever so slightly shorter, or however they make up that difference. And to bring that in and tighten these back up. Not super common to be needed. I think out of all the engines, I don't know, I've probably built 100 engines over the years of different types, and I think I only had 2 that I really needed to properly go to a shorter chain on because there was just too much slack in the system, with the exception of a small block Mopar. Every single one of those is loose. You can't get a shorter chain, so they actually have a add-on OEM part that I think came out for the Magnums, but it fits on the older ones too, that's actually puts a spring-loaded chain guide in. So it's got a chain guide similar to like an overhead cam setup. The overhead cam's got multiple guides, and it's just got kind of a spring here that then adds pressure to the chain to make sure that it's always pulled tight. And actually that is a great setup because it takes up a ton of slack on a small block Mopar. Like so much slack that it would actually be considered junk on something else. This was at least a thing 15 years ago when I was doing a whole bunch of them. And these were actually getting kind of hard to get. So I don't know what the situation is nowadays. I've thought about trying to design something like this to add to my Oldsmobiles, not because that the chain is loose, but because if we can add just a little bit of tension, we can control it just that much better. And what I mean by controlling it is because our slack, the way that it's moving between acceleration and deceleration, I mean, we could be getting a couple of degrees of variation in our camshaft versus our crankshaft, where we're ending up with just plus minus, where, plus being, we end up with, we advance or retard on the camshaft. And the way that these spin, we're going to end up with the advance in a decel situation and the retard on an XL situation. Now, because we're pulling it tight on this side and we have our slack here, what we're going to have is the cam could turn in the correct direction towards rotation because we take slack away from here and add it here. So actually the cam is lagging behind the crankshaft, versus when we go to decel, it's going to be the opposite. So this is where, usually we're end up timing our cam where we're just kind of holding, even because there's no tension in the system kind of a thing, and we just want to try to minimize as much of this. I mean, honestly, it's variable valve timing is what it is. I mean, newer cars there, they got, like a newer LT style GM engine does this advance and retard on the camshaft hydraulically, where it's actually changing that so that it can build a little bit more power, either low end or mid range, high end kind of a thing, where it's moving around. And that was something they designed and probably did lots of dyno testing with to see, at what RPM should the camshaft be at in relation, just to kind of maximize, low to mid range power kind of a thing. But the big thing is like we're building a performance engine. We don't want it just willy-nilly going wherever it dang well pleases, because especially if you get into like a steady state RPM, like say you're cruising down the highway, like you're gonna have a slight accel, slight decel. You may not notice it in the car kind of a thing, but it might be enough where it's actually just kind of rattling back and forth in there if the timing chain is loose enough. And it's just not good for the engine as a whole, but it also is just creating a whole lot of unnecessary movement in the system. So we really want to make sure that our timing chain, gears, or belt are all set up so that we have as little lash in the system as possible. Now once we've got the energy moved up to our camshaft is rotating in sync with the crankshaft, we need to know what our cam is actually doing. Now a cam is just a shaft that has an eccentric lobe on it. This lobe area is what creates our valve lift. This area around the bottom that is not our lobe is called our base circle. And our base circle is just the area of the cam where valve is closed. And our lobe is valve opening. So I'll start with the base circle because this is where nothing is happening as far as that valve is concerned. Depending on the system that our cam utilizes for controlling lash in the system, we've got two different types. There's solid and hydraulic. These are the two different methods, and solid being nothing moves. We're actually going to have a set amount of lash. Lash being just space in the system where our parts are not touching each other. Hydraulic, our parts are always touching each other, and it's just the oil pressure that keeps them pushed in contact, but not so high that it actually causes a valve to open with that pressure. So what here is that we have basically zero lash in the system because all of our parts are touching. And an example of a solid would be typically if you get a camshaft, you're going to have something that says, say, 1824 for lash. Well, what this to be is that we're talking 18 thousandths of lash. So if you take the feeler gauge and you put it between the valve tip and the rocker arm, or if we're talking overhead cams with buckets, you put it between the camshaft and the bucket, or between the camshaft and your rocker follower, whichever that your type of engine refers to that as. We're going to want to be able to stick an 18 thousandths feeler gauge in there, and they'll probably specify whether it's a cold lash or a hot lash. The cold versus the hot is just taking into the account of the expansion of all of the parts being like the entire engine. Because the block and the head they are going to expand and contract with temperature. So is our timing set, our camshaft itself, our push rods, our lifters, our rocker arms, our valves. like everything is going to expand and contract with temperature. So this number changes based on whether you're setting it cold, not running, or whether you got the engine up to operating temperature. That number does change, so your cam will specify one or the other, if not both, as far as lash settings. So, and then having the two numbers here, it's going to be 18 for the intake, 24 for the exhaust. The reason that the exhaust is usually bigger is because our exhaust valves run hotter, and therefore they grow in length a little bit more than the intake valves do, and that makes a difference there. There's just more heat in that part of the cylinder head. Now for our hydraulic systems, since we're running zero lash, it's not just, say, tightening up your rocker arm until your pushrod bottoms out and just has no more wiggle. That would be zero lash if we're using a solid system. It's also zero lash if we use a hydraulic system. However, because we're wanting to use the hydraulic system, our lifter has a couple of parts to it. So there's like a top portion that's got the cup that the pushrod rides in. And then there's a couple of, well, there should be one oil disc in there, I believe. And then a spring. Now this usually has an oil port of some sort in the side. And that's getting oil supply from the block or the cylinder head or whatever, because even overhead cams sometimes have the lifters. They sit down the head and they push up on the follower / rocker arm to hold it tight against the camshaft. So there's a couple different ways that all this stuff goes together. It depends on the engine. But it's being supplied oil pressure from the engine, and that just fills up this reservoir space between this disc and our cup that's holding the push rod, or that's a pin if it's a overhead cam follower, because it's got a pin sticking out the top to push on the rocker arm. And we're just filling that system. The disc has a metering hole in it. It's a fairly small hole in the side of the lifter. And we're just metering the amount of oil that can get in there and filling the space so that our cup on the top can't move up and down inside of the lifter itself. But when we're first putting the engine together, if it's an overhead cam setup, you really can't adjust anything with that beyond being able to add shims in the hole below the lifter body. Therefore, raising it up, therefore depressing the cup further into the lifter. That's one way to adjust it to a tighter setup. Otherwise, with a pushrod V8 system, we're actually got our rocker arm up on top. That's then we're tightening it and pushing down on the pushrod to push it farther into our lifter body as well. It's accomplishing the same thing. Typically, we're going to be talking we want a quarter to half turn when we're talking V8 pushrod stuff. So all that is we're holding onto our pushrod, we're tightening our rocker arm, and as soon as all the up and down slop goes away in our pushrod, it means we've finally got the pushrod to hit the cup, but the cup is still at the top of the lifter. Then we'll turn our rocker arm, polylock or nut, another quarter to half a turn to depress it into our lifter a little bit. Then when the engine runs, that fills with oil. It kind of locks everything in place. They're very difficult to compress after that. That's why it's able to open the valve. And that's because of the metering hole in the disc. It's basically locking the oil in place. It lets it flow in, but it doesn't let it flow out very quickly. So it locks it in place so that while the engine is running, it's holding in the correct position to open and close the valve without having any lash in the system. These can be set tighter. I think the argument is depending on how good the lifter or what that metering plate size actually is that when you get into large performance camshafts that the hole is probably still too big, or what's happening is we're getting spring pressures that are big enough that we're collapsing our hydraulics trying to keep our lifter on the camshaft lobe. So if you run it tighter, it can only collapse a little bit. But on that side of it too is that you can also get into situations where it's not in its correct range and maybe it'll lock and you're gonna get slop in the system anyway, or it's not good for the lifters. Like, you can just run into problems. The quarter to half a turn is a good place to be. I prefer to be to the quarter turn side. We're just barely depressed in there. We make sure we get plenty of oil to fill it up. And that quarter turn buys us just a little bit of space to take up wear in the system over time. And because we're building a performance engine, it's not like it's going to be seeing 200,000 miles of use. We're probably not going to see that much wear in the system before, it's back apart just to check on it, kind of a thing. But that's the benefit of a hydraulic over the solid, is that you've got no lash, so you don't have noise from the valve train. It's got its own built-in way to take up wear over time. And it's just overall a zero maintenance system at that point. Solid cams, on the other hand, we have our initial lash that we set. But it is adjustable because we're setting it. Now, why we might want to adjust the lash depends on what the engine wants. So let's say, we picked, a cam that's got .256 degrees of duration at 50 and 264 on the exhaust. At 50 being at 50 thousandths of lift. Well, if we have lash that is our 18 and 24 like it was before, but our cam, so we've got this duration and let's say it's 550 and 570 lift. So these are how big our lobes are from base circle to the top of the lobe, after factoring in the rocker ratio. So that's what we're going to see for valve lift. Well, if this is what the cam is spec'd at, what we actually have is subtracting our lash. So we actually only have 532 and 546 lift at the valve because our lash is being taken away from that. This duration number should be factored off of that lash setting. Now, let's say this cam is a little too big for our engine. We can increase the lash. But what's going to happen when we increase the lash is we're both going to reduce our valve lift because there's more slop in the system. Slop being lash. And we're also going to reduce our duration. And that may be kind of hard to think about, but it's like, so if we take our base circle and our lobe and put it into a graph form, we've got our flat base circle, and we've got our lobe back to our flat base circle. I've drawn an asymmetrical camshaft lobe here, which is a thing. They're not always consistent, but there's symmetrical and asymmetrical. Most stuff is symmetrical. Oh, that looks much better. So let's say that this is what our cam profile is going to be with a hydraulic system. Since there's zero lash, it is going to be running exactly what this profile is. And this lobe in a hydraulic, if we put the same lobe on a hydraulic as we do on a solid, these numbers are going to be slightly different even though it's the exact same lobe, simply because we've got our lifter directly on this line to open our valve, versus when the lash is factored in. I should use a different color. We've got our lash is doing this. So this is our lash take up. So you can see when that lobe profile starts to actually open, we first have to take up our lash before the valve actually opens. So we're ending up with a cam lobe that's from there to there in opening instead of being from here to here. So that's making a different duration number. And it changes the overall duration number because there's an at 50 number and then there's a advertised number. And the advertised is always whatever your seat to seat is, or maybe it's measured at a 2/1000ths of valve lift opening. So for this at 50 number, we'd probably have like a 290, I don't know, I'm just making stuff up here, 292 and a 300 advertised. So what this is telling you is that the difference in these two numbers is the amount of crankshaft degrees. That's what these numbers are. They are the degrees of crankshaft rotation that we have between 0 and 50,000ths of lift. So if we take the 292 minus the 256, that's 36 degrees. So what that's telling us is that we've got, unless it's a symmetrical profile, we have 18 degrees of crankshaft rotation that it takes for our valve to get from the seat to 50,000ths of lift on the way opening and 50,000ths to 0 on the closing. So the tighter these two numbers are, the more aggressive the cam ramp profile is. The ramp being this little area here. So the more aggressive this is, the harder it is on parts, and the softer that is, the easier it is on parts. You can think about it like opening and closing a door. A soft ramp profile is going to, open it slowly, close it slowly. An aggressive one is going to be like flinging it open and slamming the door shut. Obviously, the door that's open and closed nicely is going to be easier on the door and the frame versus one that's being slammed all the time. Now, circling back to our last setting, this is adjustable, so we can either tighten or loosen it. So I start out talking about loosening it because maybe our cam's a little bit big. So what that's going to do is we're actually going to add a few thousandths here. And that makes our cam lobe that the lift lobe section that it actually sees at the valve becomes smaller. So if we increase, say, 0.6 of lash, so we're going to 24 and 30, which is really loose. Probably don't want to run stuff that loose, but this is just an example. You know, we're going to end up at 6 is it, so 526 and 540 for our actual lift. But as you can see down here on the drawing, we're actually just ever so slightly smaller again. So our at 50 duration is probably going to turn into like 253, 261 at 50, because we've just effectively made that camshaft smaller by increasing lash. We can also do the opposite by tightening lash. And now we've made our camshaft bigger because we're utilizing more of that ramp on the way in and the way out. So now we've probably increased our valve lift. And let's say we went the other way. So now we're going down to 12 and 18. And now we've increased our valve lift. We're also going to end up with a little bit more duration out of it. Just because of where we're starting to put our lifter in contact with the cam to open all the parts. So this is a real interesting thing to actually play with on the dyno, because you are making a direct effect to the camshaft without actually having to take everything apart and change the cam. And sometimes the result, the dyno will always tell you what the engine wants, because it's either going to make more power or it's not going to care. And when we get later into a dyno testing video, we'll go over a lot more of that stuff, because the dyno's kind of the final say about whether you're doing the right thing or the wrong thing. But the cool part is when you have a solid setup and you can do back-to-back dyno runs, this is something that can be adjusted in a matter of popping the valve covers off of a V8, readjusting a lash, and you can do another dyno pull in, say, 20 to 30 minutes, and it doesn't cost anything other than the time to do it. So it's pretty cool to be able to play around with this stuff and see whether something cares. The ramp profile is not the same on all cams, because all of the actual lobe, it's part of the lobe shape, and there's all kinds of different types of lobes. But there are different types of different aggressiveness of ramps and lobe sizes that do determine what you can use as far as the type of cam. So really we've got flat tappet and roller. So flat tappets, just to draw a super old school one, is basically just like that. The cam pushed onto this not flat surface. There's actually a crown to this surface, and it rides offset on the cam. With flat tappet cams, the lobe actually has a taper ground into it. It's obviously not this aggressive, but there's a taper on there that then rides on this crowned surface on the flat tappet to make sure that it spins so that it doesn't make just like a wear groove where they grind each other together. So it needs to spin to be able to let oil and stuff up in there for lubrication and stuff. And it also spreads out the load so that you're not just wearing on one tiny little point all the time. But the flat tappet can only be so aggressive because if you think about it, traveling along onto this ramp, you're kind of like pushing a corner into it. So more modern lifter, the hydraulic lifters like we drew earlier are just more squared off. It's the same thing, got a little bit of crown. But if they're riding on this lobe and it starts to open, it can only open so aggressively before this sharp corner digs into the lobe. And it's not as aggressive in real life as this is trying to visually show you here, but we're just, our cam lobe is coming around, our lifter is fixed, so it's kind of trying to push up into it and make it do this motion. Well, it can only get so aggressive on that where it ends up contacting the corner and we've got a problem. So flat tappet cams are always lower lift, softer ramp angles. Now you can get fairly aggressive ones. Solids definitely get into significantly more aggressive profiles than the hydraulic ones do. But there's still a limiting factor there, and it's mostly due to our ramp in area. Once it's up on the lobe, you can be a lot more aggressive with it because we're already riding up higher onto the lobe as it goes around up in this area. But it's our getting it off of from the seat up to starting lift is where that really comes into play about which type of cam it is. Now with a roller, we've got our lifter body and it has a wheel on the bottom. So this wheel rides on our cam lobe, and even if I just come up here and I draw a wheel on the side there, it's pretty easy to visualize that this is going to have a much easier time going up and over that lobe, and it's not going to have any corners pinching, and it'll, because of the size of the wheel and the size of the lobe, we got two bigger arcs coming together where they can kind of go over a lot of stuff. You can kind of think about it if you're aware of like the off-roading world. Bigger tires go over things easier because they have a larger diameter. They can climb up and over other large things easy. Therefore, our roller cams can get way more aggressive on our ramp in and ramp out. And that's where if we've got, let's say, if we keep using our example up here, our 292 versus our 256, on a roller cam, those can get tightened up, or maybe we've got a 280 versus our 256, or maybe even tighter. But the big thing there is, if you look at that, like we ditched 12 degrees of crankshaft rotation in this area where we still got the same, everything up here is exactly the same. So if you're drawing these lobes out on graph paper, the number of squares below the lobe line and above baseline, the bigger that number is, the more valve open time we actually have. Now, I mean, the time in crankshaft degree rotation might be exactly the same, but the more squares we have are going to translate to the valve is open longer at a higher lift, the more squares we have on our graph paper under the lobe kind of thing. So that is area under the curve. Because we can have two different lobe profiles that have the same advertised, the same at 50, but because the shape is different above 50, they can make pretty drastically different power, because one valve, say, averages a 200 opening, like an average lift of 200 during the time, but the other one might average 280 of valve lift opening. Well, when we get into our cylinder head topic, the amount of airflow difference in that 80 thousandths is pretty big. But it's not just happening at these airflows. We're having the valve up at higher lifts, which means higher airflow for longer, even though a whole bunch of our cam specs might be exactly the same. Oh, cams get kind of crazy. There's just so many different things to kind of talk about and go over here, and every one of these things has a very big effect on the performance of the engine. Like the camshaft is probably one of the most important things about picking the right one for the application. The running joke in the engine building worlds there is bottom of the page guys. Guys that go shopping, whether it's on, their Summit catalog or whatever they shop out of that shows up every month there, and when they pick out the cam, they just open the page, look at their make and model, and go right to the bottom and pick the biggest cam. That is very rarely the correct answer. Especially with the technology that was available 20, 30, 40 years ago, very much the wrong answer. More modernly, especially when we're getting into roller cams, and because of being able to get way more aggressive on profiles and stuff, that's still not the answer. I'm willing to go a little farther down the page, especially for street applications, but it doesn't exactly have to do with the size of the camshaft as far as it being put on the page based on advertised duration. Why I'm willing to go farther down the page is because of our roller cam profiles. And as we talked about, the roller cam can be way more aggressive in the ramp area without causing a ton of wear and tear on parts. This aggressive ramp is really the secret to what I'm about to explain, and that is because with our flat, say we got a flat tappet, and we got a 236, 242 at 50. It's probably gonna, let's see, a cam that size, probably gonna be around 520, 530 lift. And let's see, it's probably gonna have like a 270, 278 advertised duration, just as an example. Now let's say we've got an engine together. This is the cam that has been in it. We like the power it makes. We like how it behaves. Now don't underestimate the word behaves. That is actually very important, because your camshaft is the brain of the engine, and all of those things we've been talking about decide the behavior of the engine. Now, let's just assume that we like the power this cam has been making in the engine. It is, however, a little rough at idle, low speed, light throttle accelerations, maybe not that great. It doesn't get terribly great fuel mileage in a cruising scenario because you end up needing to use a little more throttle because it's just not very efficient with the way it's utilizing its air and fuel, because the cam duration's a little bit on the big side for the engine because it's a smaller engine, and it just there's some things that we don't really like that much going on here, but overall it's not a bad cam. Now if we go to a roller, and we can pick out a cam that is the exact same 236, 242 at 50. So really, this number, we're picking the same at 50 number. So we can assume that we're going to be very similar in actual performance out of the cam as far as in the power band type of behavior between these two cams. However, at that duration, we probably got a 560, 575 lift. So now these two numbers together tell us that our roller profile has a lot more area under the curve than our flat tappet does, because we've got more valve lift in the same at 50. So once it's already like valve is opening, that's the direction we're going, or the valve is closing, that's the direction we're going. We're into the meat of that profile on the graph, and we're going to a higher lift along the way. So we got to draw our base circle and our flat tappet profile. Versus our roller. So you can see these 2 points here are at 50. Did not change. They are exactly the same on both cams. Same. But because we're higher lift, we've got way more area under the curve with that. But now the next part of that is our advertised duration. Because we're roller, because we're more aggressive, we might be down to a 260, 268 advertised. So we've shortened our actual cam size, seat to seat on valve opening, by 10 degrees on both lobes. That means that the valve is closed for 5 degrees longer on both ends of the lobe. So as far as our exhaust goes, we're on our power stroke, pistons coming down. The exhaust stays closed an extra 5 degrees of crankshaft rotation. That's making our power stroke longer. It also closes our exhaust valve 10 degrees or 5 degrees earlier and opens our intake valve 5 degrees later. So where that's coming into play is where we've got overlap. Overlap being we got intake lobe, an exhaust lobe. This area is the overlap. Overlap is important because the exhaust gases are exiting the cylinder at a very high velocity, and we want the intake valve to open up at a proper time where that velocity and inertia of the exhaust gas leaving the cylinder helps pull the intake in a little bit. Almost kind of like a self-supercharging effect, if you will, where, you know, the one leaving is helping pull the next one in. Now, if this, big cams, this becomes fairly big, and it can dirty up the air-fuel mixture because it might be where the exhaust loses too much velocity and then leaves some exhaust in the cylinder. Or it's still got high velocity, but now it's sucking fresh air and fuel out the exhaust valve because it's still open when it's starting to fill the cylinder up. This is going to vary based on cams because it also matters where each lobe is at, because there's the middle of each lobe, and that's going to be lobe separation angle. Angle being just the number of crankshaft degrees between the center of both lobes. The closer they are together, more overlap. The farther apart they are, the less overlap. But for the sake of our camshaft comparison here, we're going to assume that the lobe separation angle did not change. They have the same LSA, and our overlap isn't going to change other than the fact that it got a little bit shorter on both sides. So where I'm going with this is that our flat tappet cam had some drivability, issues at low RPM. There's a chance that that was being caused by too much overlap, and it was just we were losing efficiency at low RPM because of it. So we go to our roller cam and that advertised duration gets shorter. It means we're reducing our overlap even though the lobe separation angle didn't change, and we're going to be cleaning up some of that dirtiness at lower RPM. But that's not the end of all our benefits either. We've also still got that 5 degrees shorter on our intake closing, which then makes our compression stroke longer. So really what we're ending up with by doing this swap is we have more lift, more area under the curve, longer compression, longer power stroke, less overlap, and all of these things add up to this roller cam is going to make significantly more power than the flat tappet did. It's also going to idle smoother. It's going to be better at low and mid-range RPM before it's like on the cam where it's really into its peak efficiency. And there's almost no limit to the benefits we're going to see from this cam versus that cam. This is why I'm a big proponent of roller cams. Not to mention the fact that flat tappets have way more wear associated with them, and sadly in recent years quality has really kind of gone in the shitter. And if you don't have like a mainstream engine and you're relying on low production run stuff, depending on where you're getting it out of, they might not be doing a good job with the heat treatments and quality of the parts with the flat tappet setup these days. Because your flat tappet cams are cast cams, so the material is softer versus a roller cam is either a billet or a forged core. So it's just harder in general because of it's got hard rollers that run on it, so they both need to be hard to minimize wear, versus the flat tappet is, you know, the soft cast material because it needs to be able to wear in and maximize the contact patch against your lifters. But if the lifters were ground poorly or if the cam was ground poorly, they end up causing more friction, which then causes wear, and it'll take the cam and the lifters out and put a bunch of material through your engine that you don't want. It's still by far the least expensive option as far as putting a camshaft into an engine. Just because if you have a flat tappet cam engine and you want to go roller, you better be planning at least $1,500 to $2,000, maybe more, to do a proper roller setup, because you need the cam, the lifters, different push rods. You better have roller rocker arms already, or you're going to need them. And you need to change the springs. Your cylinder head might need work to put those springs in. It's one of those things that really snowballs. So when you're planning your engine build, you better plan and pick one or the other right off the bat, because it's going to be expensive either way, and it's only more expensive if you build it with a flat and then end up needing to go roller later because you ran into problems with the flat, or you already spent the money on the flat and then you still got to spend all the money on the roller anyway. So it's better just to plan for a roller right off the bat if that's what the end goal is going to be down the road. Now, for less than super popular setups, a great example of this would be my Oldsmobile. There's two types of roller cams. There's a hydraulic and a solid roller, just like there's a hydraulic and a solid flat tappet. And just like the flat tappet is less aggressive than the roller, the hydraulic is less aggressive than the solid. Now, I've got a situation with my Oldsmobile stuff where the hydraulic lifters that are available are in the not really great quality category, or at least they haven't been. I have heard some stuff that there's some newer stuff in the last couple of years that is better. But the workaround for this in a street application is quality solid lifters and a hydraulic roller cam profile. And that may sound weird, like it doesn't make sense, but what we're doing here is we're using the hydraulic roller because we need the roller for the quality of the cam, so it's the hard core, so that we can run a roller lifter on it. You cannot run a roller lifter on a flat tappet cam. And that's because of that taper on the flat tappet versus the roller is squared up to maximize surface area. Don't even think about trying it. But that's the same when you're talking roller to roller. What's different is we do the hydraulic roller cam. We've got our softer, a little bit softer anyway, ramp profile, so that's a little easier on parts long term. It also comes in a little more progressively. But then we're using our solid roller lifter, so that just means that there's no take up. So we need to have a lash setting in there so that we're not holding valves open when they get hot, because when everything expands, it gets longer, taller, whatever. if we set it at 0 lash with a solid lifter, chances are we're going to have valves leaking when everything's hot, and we're going to lose compression, and we're going to start dropping cylinders completely because it's not making enough compression to actually run. On top of the fact that if they're being held slightly open and it does fire the compression, we're now slamming that valve face and bending something trying to seat that valve again all the way. But it can run our solids with a little bit of lash, and what I've gotten away with is 0.006 of lash. So if you remember from earlier, we were talking lash is typically like 18 to 20 range on a lot of solid cams. So we're actually running super tight. And it's okay because we don't want to be loose. If we were loose, we might as well just bought a solid roller cam anyway and dealt with the aggressive profiles and got all of the performance out of it. But because we're wanting to run this on the street and we don't want it to be super noisy, we can run this tight lash. We're getting our lifter to engage on the easy part of the ramp profile. So we're easing the lifter onto the ramp instead of slamming into it every time. And then when we close the valve, we're setting it down gently instead of slamming it every time. It just makes for an overall better street application. That's the only reason we're doing this, is for the reliability of it, because we don't want to run a poor quality hydraulic lifter. It also buys us some RPM on the high end. That's the whole reason solid versus hydraulic is there. Hydraulic is there for OEMs and zero maintenance and quiet operation. Solids are there because we don't want the deflection or the bleed down in a performance high RPM application where the hydraulics really just kind of give up and collapse. And when the lifter collapses in a hydraulic, we immediately lose lift. And it makes a ton of lash in a system that's not supposed to have lash. So solids are for high RPM type of situations. And in my particular case, Rillsville, we got the solids, so we're capable of doing the RPM. I will rev my stuff past 7,000 RPM. It's not necessarily making power up at that high because it is built around more of a street style build where we have good drivability out of it. And this 236, 242 is actually the camshaft profile I have in my engine. I don't know about the advertised numbers. It's been a while since I looked at the card, but I know this is the at 50. And the lift here is pretty close too. So that's why this is a good example. But I know that when we were testing on the dyno, if we were tighter than 6, like say you did the feeler gauge, it was like a tight 6, where maybe it was more of a 5, we'd end up losing a little bit of power on that cylinder because it was leaking. Versus if we were up at say 12 thousandths, we know our valves were closed, but we were actually down a little bit of power because it was loose enough that we were making our cam smaller and it wanted the camshaft to make power. Now, all of this needs to be considered with the engine that the camshaft is in. And that is because Cam A isn't going to run the same in engine B or engine C or engine D because those engines are different, and therefore the way that the cam interacts with those engines are going to be different. The biggest factor in this is displacement. The bigger an engine is, the smaller the camshaft acts, and the smaller an engine is, the bigger a camshaft acts. So, as a great example, like we used earlier, bottom of the page guys. Bottom of the page guys typically seem to be plain old generic 350 Chevys, and they put the biggest cam they can fit in the thing. Well, that big cam in that little engine is going to have absolute trash idle and drivability, and it might make power for a little bit of RPM, and then it just runs out of engine right when the camshaft starts to work. Versus you take that same camshaft and you put it in a 427, now it's actually probably going to be pretty decent all around. And it's going to make a much longer, bigger power band while it's doing it. So all of this really needs to be considered, because you can get into way, way bigger camshafts. I mean, there's camshafts that are in the 320 plus degrees of duration for advertised, and they're still like at or just over 300 degrees at 50. And those are absolutely massive cams for a small engine. Like, they so big they probably wouldn't even run very well. But on a 600 or 700 inch big block Chevy or Hemi, not a problem at all. So, especially when you start getting into camshafts that big, the compression ratio needs to be much higher. And then, like we were talking about, where the comparison between these two, we're gaining a little bit of power stroke, gaining a little bit of compression stroke. The compression stroke is not nearly as important when you're having a, say, 16:1 compression ratio versus a 9:1 compression ratio. Because the amount of compression to get that air and fuel to where it needs to be to burn properly, the amount of crankshaft degrees that translates into is a way smaller number at 16:1 compression than it is at 9:1 compression. Like we were talking about with our lobe separation angles, between the intake and the exhaust and how they overlap. The way camshafts are ground, those can be moved one at a time, both at a time, together. It all just varies, and I'm not going to dive too much into that. The big thing is there's arguments about how it makes power with what is actually just the lobe separation angle, so the LSA. Now, the rule of thumb, typicalness of this is closer together, so smaller number is going to be a little bit peakier power. So and wider becomes more of a broader torque curve. Now, these are generalizations. It's not going to be the exact case in every scenario, but if we're looking at like a dyno graph, the example would be, our power coming up, make kind of a nice big number, and it comes off versus, coming up a little bit earlier and more of, a power curve like that. But there's so many other factors into this that this is just a rule of thumb generalization. There's no reason you can't make either one of these power curves with any lobe separation angle, simply because of all the other factors that play in. Now, smaller, so a tight lobe separation angle might be like a 104, and a bigger one might be a 112. I've seen smaller than that, I've seen bigger than that. Really, this stuff is getting a lot into the weeds, where, unless you've got the time and the money to buy a lot of cams and really do a ton of testing with this, you're probably better off, discussing it with a camshaft manufacturer, or a builder that has had lots of experience with an application very similar to what you are trying to build to get a recommendation on one or the other. Now the intake center line is how we're timing the camshaft to the crankshaft with our timing set like we talked about earlier. So this is just the relationship in crankshaft degrees compared to top dead center of number one piston. Now I've got a cam card here that we're just going to pull the specs off. This cam card has a 109 for intake center line. Center line being when we got our camshaft lobe, where the middle of it is. And you find this and check it by going, say, from putting a dial indicator on your lifter or your bucket or wherever you can actually reach it at, and you just pick a lift number that's on both sides. So you want like an opening and a closing, and when you have a degree wheel on your crankshaft, you're then able to check both of those numbers and find the middle that way. So if we're doing this on a V8, we're going to have a pretty big degree wheel mounted to our crankshaft, and it's going to just have, you know, hash marks, timing marks, kind of a thing all the way around it, 0 to 360. Well, we got our cylinder coming up. We're going to put our number one piston all the way up at the top. That is TDC, top dead center. Now this wheel can be turned, and we're going to want to put an indicator on it at TDC. And we want that to be 0. Now finding our intake center line is we're going to then rotate it past. So it's going to be rotating this way, so it's going to be counting up, you know, 1, 2, 3, 4, blah, 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 going this way. Well, we want our camshaft to be rotating, and we're checking that lift and finding this center line at, let's see what, 90, so 109 down here somewhere. So we're going to turn it, and then our piston's going to be coming down. 180 would be our piston all the way at the bottom. So we're going to be 109 degrees of crankshaft rotation, pulling our piston down, where we're going to find the center line of our intake. So as our piston's coming down in the cylinder, like that is our intake stroke happening. So we're in this portion of the camshaft lobe. It probably already opened before we got to top dead center. That was our overlap section. So now as the piston's coming down, we're into the meat of our intake stroke. So at 109 degrees, we're hitting center. So that'll actually be what, a little bit past 90. So it's a little bit past the piston being halfway down. And that might sound weird, but it's because we're not going to close the intake until we're already onto the compression stroke, because the milliseconds that it takes for this piston to travel down in the cylinder, we're creating a vacuum, and that vacuum actually lasts past bottom dead center and into the piston actually starting to come back up. Not only just from the vacuum in the cylinder, but also from a whole bunch of ram charging effect and stuff off our intake system, which we'll get into in the cylinder head video. But the point is, we're still putting air in the cylinder even though the piston's already traveling back up. But to time our camshaft to our crankshaft, we're looking for that number to match. And depending on our timing set and where that's at, you know, we might be a little bit off, where, you know, we might do this and we might come up with 106 or 110 or any other numbers. And that's where our timing gear set, if it's got different keys, we can advance or retard with the timing set. There's also some where you'll have adjustable cam gears where you can actually loosen up some screws and rotate the camshaft relative to the gear itself. There's also setups where there's a pin where the gear gets an oversized hole and then you can use an offset bushing. There's plenty of different ways that the gear sets and timing sets themselves are designed to be able to make the timing adjustable so that we can put the camshaft where it was designed to be relative to our crankshaft. Now, if where we end up running it at is 106 versus our cam specs being for 109, then that is the camshaft being advanced. And if it's 110 versus that would be retarded. And it just means that our camshaft relative to our crank is either ahead of the crankshaft or it's behind the crankshaft in where it was designed to be. Now, much like our lash settings, there can be advantages to advancing or retarding the camshaft relative to the crankshaft as far as the performance of the engine. Really, this is something you probably shouldn't be playing with unless you're doing dyno testing or have dyno tested data to back up that decision, because it's not always the case. I've had different engines on the dyno where we have done some of this as far as trying to either move the camshaft forward or backwards to make sure that we had enough piston to valve clearance in something that had really high left cam. In which case, I think in that situation we were forced to run the cam retarded because we needed to make clearance for, I want to say, the exhaust valve. But anyway, so we were forced into moving the camshaft, and in that particular case, we ended up tight on the piston to valve clearance because we milled a little more off of the heads. We upped the compression, but the cam ran retarded, and it didn't make a power difference. It moved it like a little bit on the RPM, but not enough to really have been something worth doing. So we did not pick up power from our compression because our camshaft wasn't being ideal for that. So we lost the compression power somewhere else in the system with the valve timing. I've also had different engines where we had an adjustable cam gear. I think we had it built up where we could go plus or minus 6 degrees, and started with it at 0, right where the cams were supposed to be. We went full advance, full retarded, no power change whatsoever. It was just, that's the power it was making. It didn't care where the camshafts were at. And I really couldn't tell you exactly why that was the case on that particular engine. Although that engine, we were supercharged and the cams were still fairly small because it was a 4-cylinder that we were working on, 4 valves per cylinder. So I mean, like we were getting probably the air we were gonna fit in the cylinder regardless of whether the cam was advanced or retarded because of our supercharger. Like it was just filling it, like, yep, that's what fits. And when the valve closes, we did, whether it was 6 degrees advanced or 6 degrees retarded, we weren't getting any more air and fuel in the cylinder anyway, and it didn't change power because of that. It maybe should have made a little bit of difference on the exhaust side as far as, having a little longer power stroke or not. But at the same time, the chances are we had gotten all of the power out of our combustion cycle before the valve was opening anyway. So delaying the valve opening wasn't gaining us anything because all of the actual combustion pressure was fully utilized before the valve opened as it was. And I think that was a very unique situation. But I'm telling you this because it comes down to going one way or the other based on the generalizations, which the generalizations are advancing helps at higher RPM and retarding helps at lower RPM. However, it is very engine dependent. There's so many other factors that play into this that really you could be helping yourself, or more importantly, you could be hurting yourself, or you could be doing absolutely nothing, even with a huge swing. And unless you're on the dyno back-to-back testing this, you don't know, so you might as well just put it where the cam manufacturer designed it to be put at. I'm going to stop here with the camshaft in particular. It was really just covering the basic information. I don't want to get into nitty-gritty, super engineering technical stuff. One, because for 99.9% of you that are watching this, it's probably a huge waste of time. I feel like it'd be a waste of my time. And I also don't feel like I'm qualified to get into it any more than what we've already covered, simply because being able to adjust all those individual little bits of timing with the camshaft, I could probably do nothing but dyno engines for a year straight, doing back-to-back tests, changing one little thing on the camshaft each time so that I could really science out exactly what was happening and what was causing what. And then you go and ask me about an engine that's 50 cubic inches bigger, and we can basically take all that data and it becomes a generalization, and we're mostly just throwing it out and we gotta start over. So to really claim to be an expert, I will never claim to be an expert on camshafts. I don't have probably enough years or enough money to spend in my life to try to become an expert on a camshaft. And I would argue that probably most of the people who sell or design camshafts might not even meet what I would consider that kind of advanced level of qualification for it either. Because, who has the time to really do that? I think the best example of somebody who might be extremely knowledgeable is going to be probably NASCAR Cup teams, their engine departments, where they've probably spent multiple years testing every little thing on a camshaft for a particular engine. But you turn around and ask them guys about, hey, what do I do for a boosted big block Chevy? They ain't gonna know. You ask them about a NASCAR engine, they're probably gonna be the most knowledgeable person on the planet to ask. But again, it's relative. As soon as you start changing a bunch of, you change the cylinder head that they normally work with, and now you got to start over because it was going to change the total characteristics of the engine and what the camshaft's going to mean for it. So that's the part where I probably already wasted more time than I need to explaining that it's so hard to actually truly know about a lot of that stuff. And once we get into cylinder heads more, we're going to kind of circle back to some of this where there's give and take. well, the characteristics you can put into an engine with the camshaft can be accentuated or counteracted based on the cylinder head, the intake, the exhaust. All these parts have to play together to really, make something that's good at, that can either be good at everything or is very peaky and very good in one little particular spot. Oh, it's just like the engine is a package. I tried to push that point home in our introductory video, but this is just reinforcing that. So moving on with our valve train, up next for a V8 pushrod application is going to be the pushrods. Little more than just a stick that transfers power and motion, usually with like a ball end, both sides, and an oil passage in the middle. Oh, I can't draw a straight line to save my life there. So the ball cup end is just how it interacts with the lifter. So we have the lifter down here, and it's got its little, cup in there that holds it. That allows it to pivot and move, because the push rod to the rocker from the lifter is almost never a directly straight line. There's even some Mopar stuff where it's got a pretty heavy angle. GMV6, early mid-90s stuff, like what, the 3.1, the 3.4, very aggressive pushrod angles on those. And that's okay. The big thing is we're moving up and down here, and we want the rocker to move up and down. That being said, because it's almost never directly a straight line, because this can be angled like we're looking at the valley of the block, and this could also be where we're looking at it from the front of the block, and it's angled one way or the other. Typically, it'd probably be, if we got our camshaft here and our lifter going up at a, what's typically a 45-degree angle, but that's not always the case. They can be different angles. Our push rod might be at an angle like this to get up to our rocker arm. And again, small block Mopar, pretty aggressive on this angle here. Some of their heads have offsets where there's probably a little less, but I know small block Mopar is pretty aggressive on the angle like this. The Oldsmobile stuff's got a little bit of an angle, as do most of the other, your small block Chevys, your small block Fords, your LS, like everything's got a little bit of an angle. But the big thing is because the rocker swings through an arc, the angle changes during the lift. And because your lifter is moving up and down on your cam lobe, as your cam lobe comes around, so it moves to a different position. If we get our cam lobe here, we can end up with a different position. Well, I drew that terrible, but you get the idea. More like that. But anyway, that's okay. That's what the pushrod's designed to do. Suppose it's designed to just transfer the energy and take up any alignment changes as we're, transferring that energy into the system to open the valve. That being said, they're very prone to bending or deflection. Obviously, they'll bend to be a permanent deflection. Like if something broke and it jammed, your pushrod will fail. But it does deflect, especially when you get into these big angle situations. Your pushrod is more likely to deflect, and deflecting pushrods lose valve lift. So, typical stock size pushrods are going to be a 5/16 diameter Not all push rods have the oil hole. The oil hole is just to, like, our oil coming into our lifter and then getting in here for the hydraulic will actually be pumped up, and that's how we get oil up here to lubricate our top end, or rocker arm, or springs, all that stuff. I say springs, not because they need lubrication to function, but because they need lubrication to be cooled. Springs are metal being constantly deformed, and that deforming makes friction and it makes heat. So we need to cool it with the engine oil. Upgrades, because we don't want this deflection in our push rod, can be going to a 3/8 push rod, or even a 7/16 push rod. There's 1/2-inch push rods out there. And I believe even like some NASCAR or Pro Stock stuff uses a 5/8 push rod. And that's all just to increase the rigidity and reduce the deformation or flexing, bending of the push rod that then reduces valve lift. In this situation, the rule of thumb and the obvious choice is run the biggest push rod that you can fit. In most applications, getting up to a 3/8 away from the 5/16 isn't a problem. You might start running into issues where we're rubbing on other components, mostly the cylinder head, because depending on the size of the opening for the push rod in the cylinder head, and because the rocker swings through an arc and the lifter moves and that angle changes, it might just end up rubbing or contacting in one tiny little spot. It might rub along the whole length. You don't know, and you need to check that kind of stuff. No, I've run a 3/8 push rod in almost every one of my personal engines that I race. 5/16 is totally okay for a street cruiser, low RPM type setup. That's the other thing. RPM makes all of this worse. Everything about the valve train, like we've talked about the harmonics from the crankshaft going up and causing parts to break. Well, they're causing parts to break because as RPM goes up, there's harmonics in all of these parts too. And if all of those end up collecting in one part at one point, that's when things can break. But the other thing is the amount of cycles that all these parts go through. They have mass, they have weight. An object in motion wants to stay in motion, and when you start telling things that they need to go up and down, so they're changing directions, and they're accelerating and decelerating, and all of that is being measured in multiple times per second. And the higher we go in RPM, the more times per second that's happening. The milliseconds that all those parts have to get the job done becomes smaller and smaller and smaller. The stresses and the harmonics go up big time. And the more rigid we can make these parts, the less they're going to deform, and the more of that lift energy that's going to get from our camshaft to our valve. But yes, the stiffer the push rod, the better. And related to our oil hole, coming back to our oiling system video, the push rods is one of the places where you can meter the oil to the top end. So long as your oil to the top end is supplied through the push rod, you can get restricted push rods that have typically a 40 thousandths hole in them versus the standard 80 thousandths hole. So you're just reducing the amount of oil that can flow to the top end via the push rods. Depending on the engine, it could also be done with restrictors in the oil galley that supplies the lifters. And I'm talking each individual lifter from a main oil galley, not the main oil galley itself, because you don't want to, restrict it at one point that supplies everything down that side of the engine. you want to restrict it just at the amount getting to the lifter and going up to the top end. And as we talked about, our solid lifter versus our hydraulic also requires more oil, especially at the lifter, but we can still restrict it in the push rod, and we're going to have plenty of oil in our lifter. But if we're on a solid lifter, we can restrict it before the lifter, because the solid lifter doesn't need that oil supply to make the lifter function properly. So all we're doing is lubricating the bore that it's in and supplying the top end, so it can be restricted prior. Now moving up, we got our rocker arms. And if we're overhead cam, this is where that might start coming back into play if we have a cylinder head that does utilize a rocker arm. Now rocker arms have a ratio. Typical stock small block Chevy one would be a 1:5 ratio. Most other engines use like the Oldsmobile's a 1:6. Big block Ford is like a 1.73. There's just, you can buy rocker arms in all kinds of different ratios as well. Now what that ratio is referring to is we've got a pivot point of our rocker. We have the point where the push rod comes in. So now where our push rod comes in over to our rocker pivot, and our rocker pivot over to, if it's a full roller, our contact point with our valve. So we have our valve. So the rocker ratio is that push rod distance to the pivot point to our valve contact. So in this case, if it's 1 inch from the push rod to the pivot, it's going to be 1.5 inches from the pivot to the valve contact point. So what this also means there is that if we've got a, say, 400 lobe on our camshaft, which is gigantic actually, you know, we're going to multiply it by the rocker ratio of 1.5, and that's going to be a 600 lift at the valve. So we've got 400 of movement on this side, makes 600 on this side. Now, typically cams don't have lobes that big. Usually they're somewhere between a, I don't know, 200 something up to 300 something to get our stuff. And that's just kind of based upon our camshaft and the way the cam is designed. We want as big a base circle as we can get, but the lobe can only be so big and still fit within the bore that the cam gets installed in. We want that bigger base circle because it makes the cam core stronger, and our spring pressure and all the forces and stuff are pushing back down on that cam. So the stronger the cam is, the less the camshaft itself deflects inside the block. But we'll get into a little bit more into that later. But anyway, this is our rocker ratio. And by changing our rocker ratio, we can change our valve lift without changing our camshaft. And all that'll be doing is, if we're like looking at our cam specs, we can increase the lift, which therefore increase the area under the curve we talked about, but we are not changing our advertised duration, we're not changing our at 50 duration, Well, we are changing her at 50 duration by a little bit because we're getting to 50 quicker because of our higher rocker ratio. I mean, it's not going to be a ton, but it is a little bit. So yeah, the advertised duration does not change. Our lobe separation doesn't change. Our overlap doesn't change. But the area under the curve at overlap does change because we're at a higher valve lift while we're doing it. But this, again, is pop the valve cover off, change the rocker arms, reset them. This is something that can be back-to-back dyno tested in 20, 30 minutes. But not really typically something you normally do, because normally you should probably just know what rocker ratio you're planning on using from the get-go. And more or less it's because you're kind of picking a camshaft you want, and you're picking, you know, a rocker ratio that to utilize as much lift as you can given your cylinder head and spring combination, because more lift is more power, kind of flat across the board. I understand it's very much of a generalization, or sounds like it, but at the same time, more lift is more area under the curve, and that means more potential airflow. And I'm not exactly sure that there's a situation you'd run into where too much is too much. I mean, we got drag race stuff that's lifting, I know it's well over an inch. They might even be over an inch and a quarter now of valve lift at 8,000+ RPM. Like, it's ridiculous the forces that are going on with that. But, you know, the higher the valve lift, there's a point where it starts getting real expensive real fast when it comes to lift and RPM, and them guys are still after it because it must still be making power by having more lift. Now, as far as the rocker arm design is concerned, you know, we've got stock stamped steel style stuff on the older engines. Not great rocker arms. They're good enough for an OEM thing. They have pretty much no business inside of a high performance engine build at all, ever. The only reason I would ever even see that you'd have to stick with something like that is if it's a racing class where the rules dictate it must be a factory rocker arm. Circle Track is the only one that I know of where that's definitely the case, and the reason for a rule like that is they're trying to keep the costs down and build in a limiting point for their competitors where you can't just continuously spend money. They're trying to keep a budget into the whole series and to keep people from just kind of going crazy, because almost inevitably, it doesn't matter what kind of racing you do, at some point the more money you spend, the more likely you are to win, kind of a thing. And it sucks that you can't limit that better. It's just a difficult thing, but we're getting off topic. Hey, let's get back to full rollers. I always do full rollers. I can't recommend this enough. I'm really looking at ULS people and your stupid trunnion upgrades that, man, you got to hand it to Comp Cams. They did some great marketing on selling people those, but honestly, for the price point difference of the trunnion upgrade being, $250, either a little under or a little over, and being able to buy full roller rocker arms in the 450 range, like, you're already halfway there, if not more. And the fact that your trunnion upgrade does not get rid of the fact that it doesn't have a roller, and this is a very high pressure contact area of the rocker arm, and I really can't lose track of how many people I've know or seen engine failures on that were people did the trunnion upgrade and then they break the factory rocker arm, because while it is a pretty dang good factory rocker arm on the LS engines, it's still a lowest cost of production part. And they do fail, and when they do fail, they inevitably fail in a way that seems to always fall down, jam up a spring, and drop the valve, and blow up the engine catastrophically in so many of the cases I've seen. Maybe once out of all those failures, I've seen where somebody got lucky and it didn't drop a valve and destroy the entire engine. Really makes it sound like you should have spent that extra $250, huh? That also being said, there are some extremely low quality full roller rocker arms out there. You should be able to identify these by brand and by the weight, like visually how they look. And if you don't know what it is, as I was saying, if you've ever had a cheap rocker arm and a quality one in front of you, in your hands, it is a night and day obvious comparison. You can tell just by the quality of the way the bearing and the roller tip feels. You can see that the anodizing process was a fast job on poor quality aluminum versus one that was done on nice aluminum and done properly. It's just visually it's so easy to tell the difference. And if you want to know what the sheety ones are, pretty much anything with the Proform label on it. That is the one that sticks out like an absolute sore thumb, that this is a poor quality rocker arm. And the price of the rocker arm should tell you that, when you can buy a set of rocker arms for $180 versus, oh look, everybody else that's a quality name brand rocker arm is $450 or more. Should be pretty obvious that you're paying for what you're getting at that point. Now, if you were doing I wouldn't trust those cheap rocker arms on anything above a completely otherwise stock rebuild in place of a stamped steel rocker arm. And I don't even know if I'd really actually choose to do that myself on my own personal engine, because it's an unknown versus knowing that the stamped steel ones have survived and will continue to survive. Kind of personal preference there. Honestly, this is one point that I guess the Valvetrain in general is one point where I highly suggest you spend the money necessary to buy good parts, because the Valvetrain in general is probably one of the most important parts of your entire engine. And having quality parts there means that you're not going to have stupid failures over poor quality parts. Alright, up next is going to be our valve and spring package. I'm going to include all these parts together because they really need to kind of think about them as an assembly. Alright, so if we cut our entire valve spring package area in half, this is what it would look like. Kind of color coded everything, so it makes a little more sense. Got our valve. We've got the guide that our valve is going to ride in the cylinder head. We've got the spring seat, the spring itself, the retainer, our valve locks. And you can see the valve locks are what lock into this groove in the valve. They have a taper that then locks the retainer in, which is locked in via the spring pressure pushing up on it and being held there based on our cylinder head is going to be the rest of this all down here. The The guide is what controls our valve movement into a linear line, and our rocker arm acts on the tip of the valve to push it up and down for opening and closing. Our valve itself can be made out of several different materials. Most typical ones are a type of steel alloy or stainless steel alloy. We've also got titanium and Inconel as options as well. Obviously, the titanium and the Inconel are very expensive. The Inconel is designed around extremely high temperature applications. The titanium is the lightest weight of them all by a large amount. However, titanium tends to get beat up, but it is very good for very high RPM applications to get the weight of the valve down. Why do we want the weight of the valve to be down? Well, because it's talking about those harmonics and the inertia that we touched on earlier. The lighter the valve is, the easier it is to move and change direction. And where this comes into play is if our valve is very heavy, and I say the weight of the valve, but actually it's also the weight of the valve, the locks, the retainer, and even the spring itself to a certain point. All of that being in motion, it can actually be heavy enough, moving fast enough at high RPM that it will keep the spring compressed, and the rocker arm will start being, or the camshaft will actually start being to close, and the camshaft will actually start closing. But because all of this weight and momentum, the valve, and therefore the rocker arm and the push rod and the lifter will all actually ramp off of the cam lobe. And when it finally does slow down and change direction, it'll come slamming back into the cam lobe. And it should be pretty obvious that that turns into broken parts. Now there is a point where you can actually kind of lightly throw the valve off of the cam and gain a little extra lift. Wouldn't recommend it. This was very much a technique or feature in limited circle track applications where they were only allowed X amount of valve lift, and they literally went and designed special cam lobes around being able to kind of launch the valve train and then catch it again. Not something we want to do on purpose though. It's just, especially in the context of what all these classes are about, and the fact that 99.999% of you aren't going to be desiring a situation where that can happen, because you're way more likely to screw it up and break parts than you are to actually get it right. So we want all of our valve train stuff to always be in contact with each other, to not risk doing that. And when we factor in our rocker arm, everything from the pivot point to the valve side of things, the weight is very important. The weight from the pivot down to the camshaft is not nearly as important in that equation as far as the inertia of the parts. And the biggest factor driving into that is that rocker ratio we were talking about. You know, if we got our 1 to 1.5 rocker ratio, everything on this side is moving 50% more than the stuff on the other side, which automatically is a 50% increase in everything that's happening there, the inertia and the mass. But it's not even just that, because now as RPM increases and that speed increases, we're getting into that double the RPM, quadruple the force kind of a thing, like when we were talking about our imbalance in our crankshaft. like everything becomes exponential at a point where we start getting into crazy speeds and crazy forces going on. So lighter parts out here, big plus. On the pushrod side of the equation, heavier parts are not nearly as bad of a thing, largely because of that pushrod itself. We need a heavy pushrod to combat the deflection and make sure that it's not doing crazy things while we're trying to put all of the motion into our valve system. As far as our guides, they're typically either cast iron or bronze, or just integrated into the head, which would be a cast iron head. If it's an aluminum head, you have to have a guide insert in there. I think some aluminum heads even use a steel guide. So it's typically those three materials. There are some benefits to any of them. If it's cast iron guide makes a lot of sense because it just, their thermal expansion rates and all that. Bronze has the advantage of being a little more slippery, a little bit better at lubrication. However, it does, and the benefit, it transfers heat better. Downside is in the wrong application, it can focus all of the heat and get tight onto the valve and lock the valve in a situation where it can't dissipate that heat into the head properly, or rather it's absorbing too much heat from the head. Pretty limited on where you run into that being a problem, but it is something to be aware of. Our seats, in our retainers, in our locks, typically all tool steel. You can get titanium retainers or regular steel ones. Basically, they're a hardened steel of some sort for that stuff, and that's just to make sure that because they are a wear surface with the spring. Because like I said, when the spring's going up and down, it also spins. There's some great high-speed camera videos of spring spinning with Valvetrain and RPM stuff that you can catch somewhere else on YouTube. But the spring, when it's going up and down, it also does like a waveform oscillation inside of itself. Also super cool to see in those videos. But that's where that oscillation, like that's the harmonics of the spring and how it's moving around, and we want to reduce that as much as possible, or be aware of where that spring gets too much of that and loses control of itself. Because when it loses control, that's when the valve can start it can start getting loose and tight, loose and tight, and loose and tight in this whole assembly, and we lose control of the valve train. As I've drawn this out, this is a dual spring setup. It could be single spring where it's only got the larger outer side. There's beehive springs that are conical, where they're larger on the bottom, smaller on the top. Those are designed around reducing weight because you can run a smaller retainer on the top side, as well as the spring itself gets smaller. Really, there's triples where there's yet another coil spring in here. There are springs that have a damper, which is like a flat spiral kind of a thing in pretty much any high performance application. Kind of, if you're buying a set of springs and it has those, take them out and throw them in the garbage. They're meant to dampen the harmonics of the spring, but they also generate a lot of heat because they're a flat surface that's basically rubbing on every single spring coil as it goes up and down. They add a lot of heat into your oil system, and the benefits, whatever. I mean, typically you're going to end up going with a dual spring setup on anything that isn't a flat tappet hydraulic camshaft. You get into a solid flat tappet, you need more spring pressure, you're probably going to be in the dual territory. That territory of spring pressure is also the same for a hydraulic roller, and when you get into solid roller you need a lot more spring pressure, and this all comes back to the aggressiveness of those ramp profiles on those camshafts. The more aggressive it is, the more spring pressure you need to keep control of the valve train. The heavier all of your valve train parts are, the more spring pressure you need to keep control of your valve train. A good example of this is my Oldsmobile engine that I've been racing for the last couple of years. I originally picked out that hydraulic roller cam and with using the solid roller lifter, and we picked out a spring that was for, you know, a typical generic what would be hydraulic roller camshaft spring pressures. I think it was around 130 pounds on the seat, so that would be the valve closed pressure. And we were around, what was it, like 280 to 300 pounds open pressure, somewhere in there. Actually, I should just write that out. So if we're flat, tappet, hydraulic, we're probably going to be in the, you know, for a performance application, factory stuff can be pretty wild on how low the spring pressure is on the seat. But flat tappet hydraulic, we're probably going to be in the 90 to 120 pounds on the seat. And open, we might be, you know, low 200s. Now, solid flat, and a hydraulic roller typically will be in the 130 to 150 on the seat, and will be, say, 280 to 340 open for our spring pressures. And a solid roller, we can be 160 plus to over 1,000 in some cases. But we could also be anywhere from like the 350 plus range with our solid roller. Now, in my particular case, I believe the original set of springs was like 130 on the seat and 320 open. And it ran great like that until I did about 100 miles around Road America. And if you don't know Road America, big racetrack, lots of big long straightaways. And at this spring pressure, I ended up fatiguing the valve train system. And I'm guessing it's the spring that got fatigued out, but the fatigue on the springs didn't fail, the valve failed, but the valve probably failed because of problems with the spring pressure, or in general, the valve being too heavy or whatever, and I ended up cracking about that much of the intake valve off. I got extremely lucky where this piece dropped in the cylinder, dinged the piston twice, and then got back up above and got stuck in the intake. Extremely lucky on my part, because I still drove it another 2 miles halfway around the track to exit the track, drive it to my trailer, park it, tried to diagnose what was wrong, later moved it over to another spot to kind of show it off for the evening, and then drove it back to my paddock, tried to diagnose it some more, and then stick it in the trailer, bring it home, start it up, back it out of the trailer and pull it in the garage before I took it apart and found that chunk. Extremely lucky on my part. But after looking through and seeing that nothing looked wrong with the springs, retainers, locks, and all I had was the one valve failure. The rest of the valves looked okay, but I was at the point I didn't trust it anymore on any of the valves. And after looking through what I had, I determined that the spring pressure was too low, and I probably lost control of the valve enough to where it ended up cracking because it was floating a little and slamming shut back against the seat. And it kept doing that until it fatigued the head of the valve to the point of cracking. Now, when I redid it, refreshened it up, I put different valves in because I honestly didn't trust that brand at that point anymore. Even though it probably wasn't the valve's fault, it was probably the springs. I ended up changing the springs, and I went to 170 pounds on the seat and 420 pounds open, and I have not had a repeat problem. And I've since been to Road America, I think, twice since then. And the first time after this failure that I went back, the car ran amazing all weekend. I think I did like 130 miles of just, and it was awesome. It was probably one of the best weekends I've had at the track in just raw enjoyment of driving the car. It was great because I wasn't without problems, but it did wonderful. And I had so much fun that weekend, but no engine problems. And that was where it cycled back to, keeping your valve train under control is so important. And that is why you need quality parts in the valve train, and to have all of the parts be the correct parts you need to keep control of the rest of the parts. Another thing to consider with these spring pressures, as far as I'm concerned, is it does also have to do a lot with the amount of lift. If lift goes up, spring pressure should probably also go up. And again, that's, we increase the lift, we're increasing the momentum or the speed at which all of these parts are moving. We need to be able to rein it back in and make it reverse direction in milliseconds. And the higher the RPM, the smaller the time frame we have to do that gets, and it means we need more spring pressure to be able to counteract it and get all these parts to change direction and start closing again. Now, why these camshaft recommendations are in these ranges also has a lot to do with the lift. It's how aggressive the profiles are, but the profiles are getting progressively more aggressive because they're also getting to higher lifts while we go down this route. But as an example, if we're doing a hydraulic roller and it's, say, 550 lift, that's not a very aggressive hydraulic roller. We can be on the lower ends and not going to have much of a problem. However, if we have a hydraulic roller and it's 650 lift or more, that's getting pretty aggressive for a hydraulic setup. But at the same time, that's more lift. It's probably a cam that's designed around being at a higher RPM for its power band window, we're going to need to be shifting up into higher pressure ranges, or maybe even more than these. But there's a point where you get to enough spring pressure where you're overriding your hydraulic system, like we talked about before in the lifter, and you really need to go solid roller. And once you hit the solid roller threshold, like kind of sky's the limit, because you can have a solid roller that's 650 lift, and it's getting aggressive, but it's not horribly aggressive. But let's say we have a solid roller that's in our 250, 260 at 50 window. Well, one that's 650 lift versus one that's 800 lift and only another 10 degrees of duration at 50, obviously the profile of that cam is way, way more aggressive. And we're going to need a lot more spring pressure to keep control of the valve when we're trying to run that aggressive of a cam. Things to consider. And also, because of my own personal situation, I will throw in the application of the engine, where if you're doing a drag race setup where it's just start, go, you know what, I probably could have been on my old springs for a decade and never once had this valve failure. But because I was doing road course stuff where I was 20 minutes straight at a time, I did experience this failure, and I needed more spring pressure because of the use case scenario. Another great example of that would be if you're building a marine application. It's a sweep through the RPM, but it's also a sweep through the harmonics at each RPM. Because the RPM changes, the harmonics change. But when we're at a high constant RPM in a marine application, it is just sitting there in the same harmonic zone. And if you have an issue somewhere in the valve train where the harmonic goes through and it comes back and it's not dissipated, and the next harmonic, it can start stacking and building, kind of like air and breaking the sound barrier for a jet. The sonic boom is from all the sound waves stacking on one another till they just release. Same deal with breaking parts and harmonics in an engine. If everything's building up, it's going to hit a breaking point. So all together, we want to keep control of our valve train, because that's how we're not going to break parts. Now, as far as parts, in the hard parts themselves, locks and retainers, they need to match each other because they come in a couple of different sizes. There's like a stock small block Chevy style lock is a 7 degree. What I've drawn up here would be what's called a super lock, and that's a 10 degree. There's also what's called like a super 8 degree, which would be it's wider like the 10, but it's an 8 degree taper. And that's just the taper between the two. The different lock angles need to have matching retainers. I'm not well versed in what kind of variations there are in more import overhead cam style engines. It really doesn't matter what the actual degree is. The degree is just making a wedging effect to shove the locks into the groove of the valve and lock everything in place. So you need your retainer to match your lock. And I bring this up because a 10 degree retainer and a Super 8 are pretty close where you might be able to accidentally do it, but just something to be aware of, or be aware that if you pick a spring and it is a retainer that's only available on a 10, you can't use your factory 7 degree locks. You're gonna have to get different locks. So all the parts have to fit together properly in order to make this work. On the subject of fitting together properly, our retainer to our spring interface. They don't always fit great. We want them to fit good if we have the choice. Like, you can take a retainer, stick it in a spring, and it'll move around a little, and your engine will run like that. It's not the end of the world. Everything's gonna be in hell, but the spring's gonna like move around a little bit more relative to that retainer. I don't like that. I like where if you gotta give it a little bit of push and they like click and snap together, or there's just barely a wiggle. That is a good fitting spring, a good spring to retainer fit. I'd always go for that. Same goes for the seat on the bottom. The one I've drawn is an inner spring seat, so it locates off of the inner spring. We want a nice fit there. There's also a second style that's an outer that would locate the outside of your spring. It's going to be one or the other. Same thing there. You want them to fit nice because we want our spring to kind of be held in position. We don't want it to be doing this stuff inside of those parts because we just don't need that movement. It kind of just encourages everything to be out of control. So things to be aware of that, like when you're picking out these parts, you need to make sure that they fit together properly to have it done right. There's also different types of grooves. The most typical is a square groove based off of small block Chevy and Ford stuff that most of the manufacturers used. There's also a radius style. So if I'm drawing the valve, it's going to have just a single radius in it, but there's also a dual and even a triple, depending on what the factory one was designed around. I think the single round would be, I think LS's are that one now. The dual round, I believe some Mopars used back in the day, and Caterpillar, use that lock on some aftermarket Caterpillar stuff. And then the triple would be, I think a modular Ford uses a triple. So there are variations in that. Again, you need to make sure that you got a lock that fits your valve. And a lot of these other styles, especially when you start talking like the mod motors and a lot of metric stuff, overhead cam things or whatever, like your very specialized locks and retainers in those applications anyway. So really, you can't really pick what you get on the valve, and you're not really picking what you get for the locks, so you're getting retainers that fit that setup. Versus if you're building a typical pushrod V8, you kind of got sky's the limit. You can order parts in anything way, shape, or form that you want and pick that stuff. I really don't see that there's a benefit one way or the other. I think the radius groove argument is you'd have no sharp corners. So there's no stress risers in the valve up here at the tip. So, I mean, which is the truth. It's just I don't know that you're going to run into much situation where that's ever going to be something that is a problem that rears its head. I feel like this is a good spot for ending this video. I've been out here filming, I feel like half the day already, just for this video. There's definitely so much more that we could try covering. I mean, even part of the valve train, like just getting into a whole lot of the nuances of each individual part. Like I could probably be out here for another couple hours, but I'm gonna save a lot of that stuff. Some of it we'll get into, especially when we start talking about cylinder heads. And part of that video, I'm also planning on, we're going to be doing some flow bench and cylinder head porting stuff, and we'll get into a lot more of that stuff in that video when it comes to valves, angles, back cuts, and the head, and port sizes, and all kinds of crazy things there. But as far as the camshaft and the Valvetrain is concerned itself, we've covered it pretty good. I've kind of tried not to dive into a lot of the overhead cam stuff, just because a lot of it's the same. Some of it's different. Some engines just have certain very unique things about them. I'm not going to talk about VVTI or any of the variable valve timing stuff at all, just because that is so engine specific dependent that, you know, I don't want to get way off in left field on engine X and engine Z and engine B, and, you know, not have it really apply to anybody else that might be watching this kind of a thing. There's probably more than enough information you can find on those things about specifically that system if you need to know about it. Beyond just that, you need to make sure that the biggest thing is when you hook your timing chain up or your belt up, that everything's lined up correctly so that the computer portion of those systems can do what it needs to do. Yeah, I hope you are learning something from these videos. It's certainly a lot of things have been eye-opening to myself about how a lot of these things interact, and like I said earlier, I don't think anybody can truly be an expert on this stuff without having years devoted into just camshafts and Valvetrain stuff. Something a little more crazy about some companies that actually do that stuff. I had toured Callie's crankshaft and Shaft Tech and a couple other businesses down there in Fostoria, Ohio, years and years and years ago, like 2010. Yeah, 2010, I think. And somewhere along the line, I thought it was Callie's there, they had it's called a Spintron, and they actually have it set up with a most of an engine bolted to this machine. It's just basically a big electric motor that bolts on like a dyno, except the electric motor spins the engine, and they had a cylinder cut away so that they could shoot lasers up at the valves and literally measure with a laser the variation between the valve movement and what the actual cam profile was. And through that, they were able to tell if the valve was floating or if there was deflection in a push rod because it wasn't lifting high enough, or if they had a harmonics problem where suddenly the valve started doing weird stuff. And granted, it was 16 years ago now that, you know, I went through there, so I've kind of forgot about what the exact details were, but they were talking about one situation where they had a harmonic issue and they were tracing it back through the Valvetrain system, and I think one of them was finding a problem for a NASCAR truck team, I think it was, where they had an SB2 block with an SB 2.2 head, and something got funky about the pushrod angles, and they found out there was a harmonic with the Valvetrain because of that, and these folks had half-inch 120 wall push rods, and they were snapping them off because the harmonics were building into the push rod, and Callie's was able to recreate that on their Spintron, and they were finding that the push rod itself was deflecting almost 3/4 of an inch before it was breaking in this setup about how it was causing it. Like, the amount of crazy that can happen inside an engine is just staggering before something can actually go wrong. And it's also really crazy how small of a thing can be screwed up and it can cause an engine to fail also. It's just, it's wild. So the whole point is we try to do everything as good as we need to and better if we can to make sure that we're not going to have any problems and we're going to have a long-lasting engine build. I don't normally talk about the like, share, subscribe stuff there, but I'm really hoping that this series does really well. So if you know somebody that would be like interested in this stuff, please share the video around. I think it'd be really cool to see all of this information and stuff in this build series get out there and get used, because I, for one, as being a machinist or engine building machinist back in the day, was frustrated with customers who would show up and just didn't understand how or why things need to be done in a certain way or a certain thought process with an engine, and they just like got attached to, I have to have this specific part, or I have to do it exactly something this way because the internet said so, when it's completely the wrong information. I've had people call me on the phone and try to convince me to tell them that their bad idea was a good idea, and I'm not here for that. It was a waste of time for me, and if the customer is unwilling to understand why something's a bad idea, then I don't know, it's like the person who can't be coached. Like they're not a good employee because they can't be coached. Sometimes there's just bad customers or people who get attached to the wrong thing and they're unwilling to learn from someone more experienced, or learn from their own experiences, kind of a thing, to do something better. And I just really want this information to be out there and help people along with their builds, because the better we can all do with this stuff, the stronger the community is. And that's really what I'd like to, help be a part of with all of this. So, still several videos in the pipeline. I got to work. I'm surprised how long this one ended up myself, although I knew it was going to be a long one going in. Definitely going to be a few more that we're going to get into, and even as I'm doing a bunch of these videos, like I'm purposefully kind of steering around getting too detailed on some stuff that actually maybe once I'm through all the basic stuff, we can circle back and maybe get into some of that nitty-gritty. But yeah, we'll just see how this stuff goes. So, because it's definitely, now taking up most of my day off Friday, so I don't know, we're here. I hope everybody's at least enjoying this stuff.